Hello, my name is Professor Chukwuemeka. I'm a professor of regenerative chemical process evaluation and empirical modeling. Today, I would like us to look at dephosphorization of iron oxide ore as a way of beneficiating the ore and getting ready for iron steel making. The model we're going to look at today is similar to the one we treated in model 1 to 3. The only difference is that the final solution pH is represented by minus log of hydrogen ion concentration. During the beneficiation process, a lot of unwanted materials are being removed. In this context, we're looking at phosphorus removal, which have been found out to be a function of initial and final solution pH. The phosphorus evaluation is also obtained in milligram per kilogram. Alpha is equal to the pH of the solution, final pH solution to be precise, and it's also equal to minus log of hydrogen ion concentration. We are tagging it to alpha, the final solution pH, because we want to look at the hydrogen ion concentration at the end of the phosphorus removal process. There are two constants in this model, N and K, which are 4.25 and 3.0 respectively. These empirical constants will help us to balance the equation on both sides and then solve for the unknown. Now let us look at module 4. Here we want to calculate the hydrogen ion concentration when the concentration of phosphorus removal is 199 milligram per kilogram and the initial solution pH is 0.5. Now, on substituting these values into the model, we have 199 is equal to 4.25 bracket the exponential of the initial solution pH divided by minus log of hydrogen ion concentration, all cubed. On dividing both sides by 4.25 in order to help open the bracket, we have 4.46.82 to be equal to exponential of 0.5 divided by minus log of hydrogen ion concentration, all cubed. Now, for us to remove the cube on the right hand side of equation 2, we need to evaluate the cube root of both sides of that equation. It's only when we evaluate the cube root that the index 3 on the right hand side will be cancelled. And so evaluating the cube root of both sides of equation 2, we have 3.6 to be equal to to be equal to the exponential of 0.5 divided by minus log of hydrogen ion concentration. Having done that, we need to remove the exponential sign, and by removing the exponential sign, we get the natural log of both sides of equation 3, and that will give us 1.28 to be equal to 0.5 divided by minus log hydrogen ion concentration. Remember that 0.5 is being divided by minus log hydrogen ion concentration, and so multiplying both sides by minus log of hydrogen ion concentration in order to cancel the one dividing 0.5, we have 1.28 multiplied by minus log of hydrogen ion concentration to be equal to 0.5. And so, dividing both sides of equation 5 by 1.28, we have minus log of hydrogen ion concentration to be equal to 0.39. And the best thing to do now, because we cannot solve with a negative sign for the unknown, what we do now is to multiply both sides of equation 6 by a minus sign or a negative sign, and that will give us log of hydrogen ion concentration to be equal to 0.3 minus 0.39. And then hydrogen ion concentration will be obtained by taking antilog of both sides of equation 7, and that will give us 10 raised to the power minus 0.39, which invariably will give hydrogen ion concentration to be equal to 0.4074 per mole of the leaching solution. Now, this is the concentration of hydrogen ion concentration for the removal of the specified quantity of phosphorus we had in model 4, which is 199 milligram per kilogram. Now, in model 5, we are looking at we want to calculate the empirical formula for empirical constant N if K is known, which is 3.0, and the final solution pH is known as 0.4. The phosphorus removal concentration is 194.79 milligram per kilogram, and then the initial solution pH is 0.51. Now, when we substitute these values to the model, we have 194.79 to be equal to N, which is the unknown, multiplied by exponential of 0.51 over 0.4 all cubed. If we look at the ratio of the pH and we evaluate the ratio of pH in equation 1, we're going to have 1.275, and so equation 2 will now be 194.7 to be equal to N into exponential 1275 all cubed. Now, on evaluating the value of exponential 1.275 as we have it in equation 2, we'll get 3.5787, and so 194.79 will be equal to N multiplied by 3.5787 cubed. On evaluating the cube, that is 3.5787, we'll get 45.8327, and so 194.79 will be equal to 45.8327 N, and invariably N can be obtained as 4.25. This agrees with the value of the empirical constant even from the first model we used. The value of N has always been 4.25, and we've been able to get that by substituting the necessary variables. In model 6, we want to calculate the empirical constant K, having known that the N is still 4.25, and if the initial solution pH is 0.5 and the final solution pH is 0.4, we can get that if the concentration of phosphorus removed is 209.96 milligram per kilogram. It's pertinent to know that for us to proceed, we will need to substitute these values into the model. And so we're going to have 209.96 to be equal to 4.25, multiplying exponential of the initial and the final solution pH ratio raised to power k. Now, if we divide both sides of equation 1 by 4.25 to help give way to evaluating the value of k, we'll have 49.4 to be equal to exponential of 0.5 divided by 0.4 to power k. And if we evaluate the pH ratio 0.5 divided by 0.4, we're going to get 1.25. And so equation 3 will now be 49.4 to be equal to exponential 1.25 raised to power k. And then the evaluation of exponential 1.25 will give us 3.4903 to power k. And then finding the value of k now, we need to take log of both sides of equation 4, and that will give us log 49.4 to be equal to log 3.4903 to power k. And this can be rearranged as log 49.4 to be equal to k log 3.4903. Now, when we take time and evaluate the log of both sides, we're going to have 1.6937 to be equal to 0.5429 k. And invariably, k can be calculated as 3, approximately 3. This also agrees with its value in the first principle model, which we used from model 1 to 3, and also continue to use it from 4 and then up to this point. I want to thank you so immensely for watching and for listening, for your time. You can look at the source of this model and then see how much work has been done on this model, and also to verify a few facts the way you like it. I still remain your instructor, Professor Chuka Moye, and I want to thank you again for watching. Please subscribe to Mr. Math eLab, and bye for now. Thank you.